I'll do a quick one. Try to review this paper. Okay, we should be live. Just test the microphone real quick. Test the microphone real quick. Okay, I think we need some oomph to the microphone. Okay, we'll review this paper real quick. Well, I haven't read it myself. Just saw this like emotional video about it. Is my microphone okay? Should be alright. Okay, we'll find the robot, an agent, an AI agent to talk about this paper real quick. Okay, what's the title of the paper?
The title of the paper is Personalized Adaptive Cortical Electrostimulation, PACE, for treatment-resistant depression. If you need any more details, just let me know.
Okay, just for a sanity check, can you review figure 1 real quick?
I'm sorry, but I don't have access to the specific details of figure 1 from the Nahas et al. 2025 paper. To provide an accurate review, I would need to view the figure. You might consider accessing the paper directly through a scientific database or the journal's website to examine figure 1.
I just shared the paper with you.
Got it. Let me take a look at figure 1 from the paper and break it down for you. Just a moment while I pull up the details.
What is out of nerve? Are you there?
Thank you for sharing the paper. I understand you're interested in figure 1. However, I don't have direct access to the figure content. If you can describe the figure or share some details about it, I can definitely help.
Okay, that didn't work well, did it? Yes, it didn't doesn't have access to the whole thing, even if you let me see, 1 sec. Hey, do you have access to figure 1? Can you describe figure 1? What's up? Try it once more real quick. The paper is open source. Want to? Can you? There's something wrong. I'm still loading the PDF. Okay, can you describe figure 1 real quick? Does it? 1CD. Okay, can you actually describe it in plain language? It's called him. Sounds like. What's him? It's that specific patient. Did I refer to them as him? It's just. Okay. Yeah, I've seen one of those videos once. Okay, can you describe the paper in plain language without using any terminology? I don't know what I need to send.
All right, here's the no jargon version. This paper is about a man who had been severely depressed for over 30 years. And nothing, not medications, not shock therapy, not other treatments, had helped. The researchers tried a new approach where they first scanned his brain in detail to see exactly which areas were working differently from most people. They found one system in his brain was taking up way too much space and pushing into areas linked to mood and thinking. They then surgically placed thin electrical pads on top of his brain in spots chosen just for him, based on the scans. After surgery, they tested which spots affected his mood and thinking right away, and adjusted the settings over several months using a smart, data-driven process. Within 2 months, he no longer had thoughts of ending his life. Within 9 months, his depression was gone, and it stayed that way for at least 2.5 years. His thinking speed and attention even got a little better. The main point, matching the treatment to his unique brain layout and adjusting it based on his responses, worked when nothing else had.
Okay, can you touch on what do you mean by found one system in his brain taking up way too much space? What does that mean?
In plain language, brains are organized into different teams of areas that handle different kinds of work. In most people, these teams have a certain balance in how much brain real estate they each use. In this man, one particular team, the one that's in charge of spotting and reacting to important things, had grown so big that it was taking over territory normally used by other teams, especially ones involved in balancing emotions and focusing. So, taking up too much space means that this team's turf had expanded far beyond its usual borders, and in doing so, it was squeezing out the brain areas that help keep mood steady and thinking clear.
don't use Teams in that way. It's hallucinating on me already, I think. Where did you get the Teams term from? It's not in the paper. Just want to see if it's... just want to ground it to the...
Yeah, team was just my own analogy. The paper never calls them that. In the paper, they're talking about functional brain networks like the salience network, default mode network, and frontoparietal network. I swapped network for team, so it would make
What?
sense without technical terms. If you want me to, I can redo that bit, sticking strictly to what's in the
That doesn't
paper,
make any
just in
sense
plain
whatsoever.
language.
Yeah, just don't make up terms if you can. But can we move on explaining figure 1 real quick in plain language, but make it technical. Explain it to like an engineer, not a neuroscientist. That was actually GPT-5. Yeah, that wasn't a great response.
Got it. Here's figure 1 explained for an engineer. Figure 1 is essentially a spatial occupancy and overlap analysis of the patient's brain networks compared to population baselines. Main finding: in this patient, the salience network covered 12.4% of cortical surface area, about 4 times the average in healthy controls. The expansion was concentrated in the frontal cortex, or 35% coverage there. Impact: this enlarged salience network encroached on other networks. The default mode network lost 25% of its typical surface area, and the frontoparietal network lost 18.6%. Visualization: 1A shows the salience network in inflated brain surface views, comparing patient versus individual control versus group average atlas. You can see how atlas-based stimulation targets, BA10, BA46, overlap differently in this patient. NARIS 1B is a bar chart quantifying salience network size in this patient versus 3 control datasets, HCPD, PDC, Lynch et al. Stats confirm the difference is significant. -1C maps DMN, FPN, AMN, and DAN in the patient and group average, then overlays the patient's salience mask to show displaced boundaries. 1D quantifies how much of each network's area has been overtaken by the salience network. High for DMN and FPN, negligible for DAN. So, in engineering terms, think of each network as a defined spatial partition in the cortical floor plan. In this patient, one partition, salience, had overexpanded and was occupying sections normally allocated to other subsystems.
Can you explain figure 1 B? Which one is the current study and which one is compared? So they're just comparing it to one other study today, or what's HCP PDC? Okay, won't let me downgrade to a different model. That's unfortunate. Okay, we're not paying currently for... No, I mean we do through GitHub Copilot. This one we cannot. Well, it knows the topic much better than I do, so let's give it to Gemini 2.5 Pro. It's on about 10,000 tokens, the whole paper. We can't read it out loud. We can turn it into a conversation, so like a chat. Yeah, obviously the N01 placebo effect. Yeah, that's what I was thinking. Yeah, I think this is pretty much all you need to know about this paper. The placebo effect. The placebo effect in invasive neurosurgery for psychiatric condition is known to be extremely powerful. The patient, who has suffered for decades, underwent a highly advanced, personalized, and hopeful procedure. This creates a massive expectancy effect. I assume that's when the patient is expecting great outcomes. So essentially, it's tricking the patient into believing it actually works, and the brain just does it. We know it works. It's not a sham. Well, it is a sham in this case. I mean, yeah, invasive implant is N01, so one subject only, and then seeing these great results. Well, based on self-reporting, the patient is saying that he is experiencing joy and things like that, and they got some really emotional videos out of it. So where were we? Yeah, so the placebo effect, hopeful creates massive expectancy effect. The paper shows that his self-reported expectation of benefit, the CEQ score, don't know what that is, jumped from 30% pre-surgery to 90% post-surgery, while the acute blinded stimulation test demonstrate true physiological effects. They cannot rule out that the long-term remission is driven by a powerful and sustained placebo response. Let's just check the numbers. Credibility / expectancy questionnaire. Yeah, maybe we can explain that. That would be interesting. And the other question is if they address placebo. Did I mention placebo? No, there's a reference mentioning placebo. They do not. Yeah, so very interesting results. Yeah, they get you can watch the videos, highly emotional stuff. Conflict of interest. Yeah, pretty much any paper just goes straight to the conflict of interest statement. You'll be amazed. But it's good that they're reporting. I know some other papers do not even report the conflict of interest properly. And normally there's a high bias to think that the conflicts of interest that you have are not relevant to the results. Well, I would say, disclose your conflict of interest and let the reader decide if they're relevant or not. But yeah. Yeah, how many times so they don't mention placebo, which they should have. How many times they mention joy? They mention joy 7 times. So the feeling of joy, overwhelming feeling of joy. It feels nice. So weird to feel. It is so emotional. Yes, it just made the patient super emotional. Yeah, obviously just the surgery will make you super emotional. What could you make feel nice? This is also the fact that there's all this clinicians and people taking care of you and asking you questions, letting you do all these tens of different questionnaires. That's also definitely will contribute to the placebo effect. It's nice that they're having equations. What on earth? The equations are for sleep quantity, preference ranking, measure of mood. Okay. Yeah, so it's quite a severe case. The patient is highly vulnerable. They're doing an implant. How many figures are there? There are only 3 figures of results. Yeah, we'll need someone explaining this to us. But yeah, just the fact that placebo was not addressed. I don't know if it's addressed in one of those questionnaires. I guess, yeah, it's that expectation thing, isn't it? The CEQ score. So there's a questionnaire for it. It's the expectation of benefit. And they do this questionnaire before and after. Considering I saw it on. Anyway, essentially figure 1 shows how supposedly this patient having a different an abnormality in the brain, even though, yeah, the evidence is, yeah, I don't know. So they're comparing it. I mean, how does it compare to variability, to natural variability in other patients? Let's actually try turning this into and let's turn it into a detailed conversation between let's make a neuroscientist and an engineer. So neuroscience expert clinician and a biomedical engineer. Let's see what it does, because we do have a text-to-speech model, but it's more complicated. It can do more than one speaker, which is nice. A native yeah, so multi-speaker.
Ready to make something amazing?
What kind of problem could we solve?
What kind of project are you thinking of?
What idea do you want to bring to life?
Ready to build something awesome today?
Let's do speaker 1.
What do you want to explore?
Okay, we get the 2 voices. So it's setting up a scene and everything. Then we don't need the scene, we'll just do the chat. We have to change the names of the speakers. So I have Ben Carter and Anya Sharma. Those are obviously made up names. And it will do like describe the style. A detailed conversation between a neuroscience expert, clinician, and biomedical engineer discussing a paper. Let's run that. Let's see how long does that take. I might be moving on after this. Well, because essentially, yeah, I mean, publishing a paper like that without addressing the placebo. And we had some other issues as well. Blinding during optimization. There's also, losing my voice, paper operates on the premise that the expanded salience network is a causal factor in patients' depression. While the treatment success supports this, it's also possible that the network expansion is a long-term consequence of the illness or compensatory mechanism. The study doesn't definitely prove causality, although it proves strong correlation evidence. Yeah, so essentially this brain abnormality might not actually cause depression. It could be actually the result of the diagnosis, not the cause for it. And then there is a blinding issue. So the patient was blinded to the parameters of the 5 settings he toggled between each month. However, he was aware he was receiving active stimulation. So there was no sham stimulation. There was no, so more importantly, The acute effects of stimulation were often described as it's a joy I feel in tune. It will be very difficult for the patient not to notice when setting was having a positive effect, potentially biasing the subjective preference ratings that fed into the bias tuning algorithm. Tuning algorithms. But I think, by the way, I think when the chat is, the discussion is ready, the podcast is ready, they will just start talking. Yeah, we need the link for the paper as well, don't we? Pop the link to the paper. It's the paper we're talking about. It's a preprint. So not peer-reviewed. Big no. Oh no. Not a peer-reviewed paper. Well, we don't care if it was peer-reviewed or not. We know the peer review process is highly biased anyhow. Yes, so this patient had an implant. So highly invasive procedure that supposedly made them feel the joy of life again.
Did you see it? The Nahas paper on personalized adaptive cortical electrostimulation. It just dropped. I've been reading it all morning. It's stunning.
I have it open right now, Ben. Stunning is the right word. To take a patient with a 30-year history of severe TRD, someone who's failed everything we could throw at him, and bring him to full, sustained remission for 30 months, it's the kind of outcome we dream about.
Exactly. But from my side, it's the how that's blowing my mind. This is the holy grail of BME in neurotech. They didn't just implant a device. They built a complete, personalized, closed-loop therapeutic system. The integration is elegant.
Break it down for me from your perspective. You see the engineering elegance. I see a single miraculous data point I'm desperate to replicate.
Okay, so look at the three pillars. First, the precision functional mapping. They moved past the old atlas-based, one-size-fits-all targets. They found a quantifiable individual biomarker, a 400% expansion of the salience network. They didn't just say, stimulate the PFC, they said, stimulate the border of this patient's uniquely oversized network. That's a massive leap.
I agree. That part is groundbreaking. Identifying a potential brainotype for TRD is a huge step for the field. But, and you know this is my biggest reservation, it's an N of 1, a single patient. We have no idea if this salience network expansion is a common feature or if they just got incredibly lucky and found the one patient in 1,000 for whom this specific pathology is the driver.
I hear you on the generalizability, and we'll get to that. But you can't dismiss the rigor of the target engagement. Look at Figure 2. The post-op stimulation mapping is the perfect validation. Stimulate the DMN contacts, you get joy. Stimulate the FPN, you get clarity and focus. The effects were immediate, reproducible, and network-specific. That tells me this isn't just a happy accident. They were modulating the exact circuits they intended to, and those circuits produce the expected behavioral outputs.
That part is incredibly compelling, I'll grant you. It's a powerful argument against a purely psychological placebo effect, at least for the acute response. But the long-term remission, that's where the clinical picture gets murky. This patient went from decades of hopelessness to being the subject of a cutting-edge, hyper-personalized procedure. His expectation of benefit, the CEQ score, shot up from 30% to 90%. That's a massive placebo-enabling context. The intensive monitoring, the daily interaction with the research team, all of that has a therapeutic effect.
But that's where the second pillar, the Bayes tuning, is so brilliant. They didn't just find a good setting and stick with it. They used Bayesian optimization to systematically and efficiently explore the massive parameter space, frequency, pulse width, amplitude, contacts. Instead of the clinician guessing and tweaking every few weeks, they had an algorithm learn the patient's response surface in real time based on daily feedback. It's adaptive. It can account for neuroplastic changes or tolerance over time.
It's a fantastic approach to optimization, far better than our current trial and error method, which can take years. But again, the input for that algorithm was the patient's subjective reporting. He was blinded to the parameters, yes, but not to the effects. He reported feeling a joy with one setting and focused with another. He could absolutely tell which settings were good. His preference rating, which fed the algorithm, would be heavily biased towards the settings that produce those immediately palpable positive feelings. Is the algorithm optimizing for long-term antidepressant effect, or is it optimizing for immediate feel-good sensations?
That's a fair critique. The objective function is a composite, but it does lean on that subjective preference. Maybe future iterations could incorporate a more objective biomarker like EEG or wearable data. But let's talk about the third pillar, the hardware. They used standard cortical paddles. They didn't have to invent some crazy new deep brain probe. This makes the surgical approach less invasive and safer than DBS, which brings me to their claim of scalability.
Ah, yes, the claim that it's scalable, safe, and cost-effective. Then let's be realistic. This protocol is the definition of unscalable right now. It requires an elite team of neuroimagers, surgeons, data scientists, and psychiatrists. It requires extensive, high-quality fMRI data, a multi-day ICU stay for testing, and intensive daily follow-up. How is that scalable to the millions who need it?
From an engineering standpoint, every revolutionary technology starts this way. The first MRI machines filled entire rooms and required a team of PhD physicists to run. This is a prototype. We can automate the PFM analysis pipeline. We can streamline the surgical planning software. We can reduce the scan time with better sequences. The Bayes tuning can be run from an app on a phone. The cost of the hardware will come down. What they've provided is the blueprint. 10 years from now, this could look very different.
I hope you're right. But I worry the headline, Cure for Depression, will overshadow the nuance. What this paper really shows is a powerful proof of concept for a subtype of depression. The next step isn't to roll this out. The next step is to use PFM to scan 100 TRD patients and find out how many even have this salience network brainotype.
Exactly. It gives us a clear research path. It's a hypothesis generator. Find the biomarker, then treat it. And think about the implications for non-invasive methods. If we can confirm this SN-DMN border is the key target, maybe we can hit it with precision TMS or focused ultrasound. PACE becomes the gold standard for validating targets that other technologies can then aim for.
Now, that is an exciting and realistic path forward, so we're in agreement. It's a landmark study, a tour de force of personalized medicine, but it's not a conclusion, it's a starting pistol. It's the beginning of a tremendous amount of work.
Absolutely. A beautiful, elegant, incredibly promising starting pistol. I'm already thinking about how we could improve the optimization algorithm.
And I'm already thinking about the patient. I hope he's still doing well. At the end of all the data and schematics, that's what matters. They gave one person his life back. Now we have to figure out how to do it for everyone else.
Pretty much get everything we can out of this paper. I don't think there's much point going into it. I don't think they published the data. Actually, pretty sure they did not publish the data. They only published the videos. So I don't know. Yeah. Should we do another review or not? Yeah, with the algorithm tuning, optimization, whatever. Yeah, that. Well, I mean, is there a point to even discuss it, considering how strong the placebo effect to begin with? We can do another one, but yeah, we haven't touched on the last figure. You would expect it to be about the optimization, the tuning. There's different questionnaire scores, I would imagine. bit of a pain to set up. It's a bit of a pain to set up. So this is AI Studio, generates speech.
Got a project in mind?
What do you want to explore?
Ready to make something amazing?
Ready to make something amazing?
What sparks your interest?
What kind of masterpiece?
What's a skill you'd like to develop?
What kind of problem could we?
What kind of project?
What idea do you want to?
And let's do this too. We'll run it again. Running it in the same tab, so it will essentially replace the previous chat, I would imagine. And it's much smarter than I am, so and there you go. So we did one review. It was maybe a bit too positive. Ask it to be more critical. And also talk about the actual algorithm of how they're doing the tuning. It's the black line. Seems saturated already. Yeah, when you combine, there's a problem of combining psychiatry or whatever, psychiatry in this case, with a neural stimulation device. The metrics are not comparable. Those are obviously highly subjective. Those are based on questionnaires. And then, so they tune up the stimulation parameters of essentially which electrode will be stimulated and how, based on the patient's subjective questionnaire responses, which essentially things like I feel calm, relaxed, not overwhelmed. This is caused by stimulating these electrodes, and then I feel nice, feels calm when stimulating different electrodes. So like you have different parameters. So different frequency, pulse width. Pulse width is always the same. Yeah, changing the frequency of stimulation. The amplitude is kind of the same. No, in this case it's 4 milliamps. So they're essentially taking these kind of descriptions, so weird to feel, and turning them into frequency, pulse width, and amplitude of the stimulation, and deciding in what configuration to stimulate the brain. And the patient knows they are being stimulated because they're essentially selecting one out of 5 preset parameters or something. And they're not mentioning placebo effect in this paper at all, like whatsoever. He has 2 of these electrodes placed. So what is this supposed to tell? Like if you stimulate in this configuration, that will be saying I feel calm, relaxed, not overwhelmed. If you stimulate in different configuration, and say it feels nice, feels calm. So like how more subjective can this be? I don't think it can be more subjective than this. One subject only. The only data they release is these highly emotional videos of essentially recording the patient, essentially digging in, asking the patient, question, how do you feel? And how do you feel right now? And how would you describe this emotion? So this is essentially what the questionnaires are doing as well. But then mapping that to the frequency of stimulation, the pulse width, amplitude of stimulation, and the arrangement of the electrodes, like which electrodes are a cathode, which anode. So in this case, this way the stimulation will be happening on the red electrodes and the cathodes acting as ground. And then they change the configuration of the stimulation based, and they essentially link it to these responses. They're not monitoring anything else, I think. Not sure if they're doing any recording. I suspect, my understanding, it's the feedback they're getting is only verbal from the patient, so highly subjective. So essentially maximizing on the placebo effect. I don't know how else to describe this kind of highly invasive procedure. Yeah, correct me if I'm wrong. Correct me if I'm wrong. Go check out the paper as well. It's open source, publicly available. As everything else we do on BioniChaos.com, so whenever we make a blog or ideally an interactive web application, it all goes on to BioniChaos.com, so go check it out. And don't forget to provide your feedback.
A clinical neuroscientist and psychiatrist specializing in treatment-resistant depression and neuromodulation.
A biomedical engineer focused on closed-loop neural interfaces and computational modeling. Anya, let's get right into it, the PACE paper. From an engineering standpoint, it's a masterpiece of system integration. The PFM-guided targeting, the cortical paddles, and the adaptive optimization, it's the full closed-loop blueprint we've been theorizing about for years actually implemented. The elegance of the Bayes tuning is what really stands out to me.
I agree. It's an elegant blueprint, Ben, and the clinical outcome is undeniably spectacular for this one individual. But my clinical skepticism kicks in precisely at the point of that elegance. The system is only as good as its inputs, and the inputs here are profoundly problematic. We're not just optimizing a circuit, we're optimizing a person embedded in a high expectation clinical trial.
Let's break that down. The optimization target was the composite score, F of X, which incorporated sleep, mood, and preference. The beauty of the Bayes optimization, specifically the Gaussian process regression model, is its ability to intelligently map that response surface without exhaustive searching. It balances exploitation of known good parameters with exploration of uncertain regions. It's a data-efficient solution to an n-dimensional parameter space problem.
And that's where the critique begins. The objective function, f of x, is a black box of subjectivity. The mood and sleep metrics were standardized by z-scores relative to baseline, which is fine. But the heaviest weight, the one that can truly differentiate closely performing settings, is the patient's subjective preference ranking. The paper shows that stimulating the DMN context produced immediate, overwhelming joy. Stimulating the FPN produced clarity. These are potent, acute, hedonic effects.
You're suggesting the algorithm wasn't optimizing for a durable antidepressant effect, but rather for a transient, desirable sensation.
I'm suggesting that the algorithm is, by its very design, incapable of telling the difference. A patient suffering for 30 years is given a setting that produces a novel feeling of euphoria. Of course they will rate that a 10 on preference. The algorithm, doing its job, will then aggressively search the parameter space around that peak. The system could be inadvertently selecting for a setting that provides a rewarding jolt, which is not necessarily the same as a setting that normalizes network function and provides stable euthymia.
That's a powerful point. The model is optimizing the proxy, not necessarily the underlying pathology, but the sham-controlled videos seem to argue against a pure placebo effect. The anxiety response to stimulating all contacts simultaneously, which subsided with sham and returned upon restarting, suggests a very real non-placebo physiological mechanism.
Absolutely. I don't doubt for a second that the stimulation is causing direct, network-specific neurophysiological effects. The issue isn't a classic placebo, where an inert innervation works. It's a far more complex scenario, an active intervention whose perceived benefit is massively amplified by expectancy, and that amplified perception is then used as the primary input to guide the therapy itself. It's a confounding feedback loop. The patient's CEQ score jumping from 30 to 90% is a flashing red light. The base tuning algorithm is essentially chasing a signal that is a mixture of genuine effect and powerful psychological context. We can't disentangle them.
So to improve the system, we'd need a more objective biomarker as an input to the objective function, something like a specific spectral feature from a local field potential or a wearable-derived measure of activity or sleep architecture to replace or supplement that subjective preference score.
Exactly. Without that, the rigor of the algorithm is undermined. Which brings me to the data itself. I was frustrated by the lack of transparency. The paper presents a compelling narrative, but the quantitative evidence is heavily processed.
What do you mean? They showed the outcome scores over time.
They showed smoothed curves. The paper explicitly states they fit the HDRS, MADRS, and MSSI data with a smoothing spline because the raw weekly scores were too volatile to accurately capture changes. As a clinician, I want to see that volatility. I want to see the raw daily mood and preference scores that were fed into the GPR. Without that raw data, we can't independently evaluate the optimization process. We can't see if the algorithm converged smoothly or if it jumped around based on fleeting patient preferences. All we have is curated video snippets and a curve fit with an R-squared of greater than 0.9. It feels more like a presentation than a data set.
I can see that. From a reproducibility standpoint, the raw time series data from the optimization phase would be critical. It's likely a limitation of the N-of-1 case study format, but it's a valid critique. What about the core biomarker they targeted, the expanded salience network?
It's a fascinating finding. Again, N-of-1. Is this massively expanded SN the defining feature of ultra-treatment-resistant depression, or is it an idiosyncratic feature of this one patient? They even show in Figure 1D that this brainotype isn't universal. This success might only be applicable to a tiny, uncharacterized subset of the TRD population. Calling the approach scalable in the abstract feels premature at best.
I'd argue the scalability isn't about the specific biomarker, but the methodology. The blueprint is scalable. PFM to find any individual network anomaly, targeted stimulation to modulate it, and Bayes turning to optimize it. The target might change from patient to patient, but the process remains. Of course, the resource cost is immense right now, but that's a technology maturation problem, not a fundamental flaw in the concept.
It's a fair point, but for now, we have a single, remarkable result from a study with significant confounds, guided by an elegant algorithm operating on subjective, unauditable data. It's a phenomenal proof of concept, Ben, but it's not a validated therapy. It's a starting gun for a decade of incredibly difficult work to see if this can be made rigorous, objective, and truly generalizable.
Agreed. The next iteration needs objective biomarkers for the optimization loop, and the next trial needs a larger cohort to validate the SN biomarker. But you have to admit, as a starting gun, it's about as loud and brilliant as they come.
On that, we are in complete agreement. Now, let's talk about the specific choice of a Gaussian process model. I have some thoughts on its kernel selection for this type of noisy biological data.
Okay. It will share the ideas it has. Should we just continue this one? Let's see the video. So they published, was it 12 videos? It's part of the study. Don't know if I can. There's a problem with the video. Did it finish downloading? Don't quite understand. Can you just generate the whole thing? Change the temperature of the model. I don't know, do we need to you can also continue the conversation, the same conversation, but just summarize the paper, the results, but also mention if there was anything objective measured from the one patient. I don't think there was, but we just need a confirmation. I don't know if we should regenerate the whole thing, maybe with different speakers, different voices. different voices. Okay. It says the conversation continues seamlessly. Okay, we're not gonna read all that, obviously. I can add dialogue. Yeah, it's editing it correctly. Yeah, it's different. Oops. Yeah, let's do neutral ones. And then it just starts talking when it's done generating, which is a bit odd. Anyway, you can download the audio. Hey, let's run this one. But yeah, essentially, I think we're done with this paper. I think we are done. But yes, might do just the last review. And if you have checked BioniChaos.com and you have any questions, do let us know. We have some stuff in the loop, in the pipeline that is coming out. With this PPG monitoring. This is obviously synthetic. I don't know if I have to say. Well, I mean, it could be real data as well. So you wouldn't know, would you? Would you? This is also based on paper results that essentially say that how the position of your body, so if you're standing, sitting, lying down, it changes PPG recordings, so your blood oxygenation recordings. So it's obviously approximation of what was in the paper. Oops. When you sit, you can do arm on the lap or arm on heart. Makes a difference. Yeah, obviously the cartoon is not great, but you get the point. Yeah, so for example, if you're standing up and you hold your arm at heart, you get a much stronger signal. When you have your arm down, yeah, you get a lot of noise and things. So this is results from this paper. We actually split the result into two sections because they're also talking about how age changes your PPG. I won't be trying to pronounce PPG, but yeah, photoplethysmography. How did I go? Any Latin native speakers? listening to this, do let me know. Yes, because we do want to collaborate with clinicians. So the rest of the paper, so essentially we split the results of the paper into two. One is the standing position, sitting down, lying down, whatever, how it affects the signal to noise ratio of blood oxygenation measurement. And that one is your age, skin tone, and obviously the lead intensity, which doesn't seem to make much difference in this case, even though I'm a bit suspicious of it. But yeah, it's just an approximation of the results from the paper. I mean, it's still better than looking at the graphs they have in the paper itself. So yeah, if you have any feedback on this, I'll pop the two tools links, whatever they're called, visualizations, animations. What are they also called? Interactive. Well, they are interactive. I'll pop the links in the chat. Let me know what you think. Funny enough, if you ask in person someone, do you prefer my voice as opposed to AI, they always say we prefer your voice. But currently, I can tell for sure that data is showing otherwise. That you actually do, that viewers do prefer AI talking. Well, probably because they're just doing it much better. Yeah, so we're reviewing this paper. I have this implant that one patient have received. So this thing is so can't get rid of this thing. No, I cannot. Do I have another? A PDF viewer? Yes, which should be better. Oh, can I get rid of that? Anyway, obviously no one's actually reading papers. No one's reading text, but we had a chat, a very detailed chat to, in this case, Gemini. And we turned that discussion we had into a conversation between neuroscience expert and a biomedical engineer, which will start playing whenever AI Studio is finishing generating. So so we have like an extended, it will be like already played a part of it, but this will be the extended version of it. Okay, we had 1 like. Thank you very much. Don't forget to comment as well. That's the most important thing. That's why we are here. Hit the desktop audio turn off before.
A clinical neuroscientist and psychiatrist specializing in treatment-resistant depression and neuromodulation.
A biomedical engineer focused on closed-loop neural interfaces and computational modeling. Anya, let's get right into it. The PACE paper. From an engineering standpoint, it's a masterpiece of system integration. The PFM-guided targeting, the cortical paddles, and the adaptive optimization, it's the full closed-loop blueprint we've been theorizing about for years, actually implemented. The elegance of the Bayes tuning is what really stands out to me.
I agree it's an elegant blueprint, Ben. And the clinical outcome is undeniably spectacular for this one individual. But my clinical skepticism kicks in precisely at the point of that elegance. The system is only as good as its inputs, and the inputs here are profoundly problematic. We're not just optimizing a circuit, we're optimizing a person embedded in a high-expectation clinical trial.
Let's break that down. The optimization target was the composite score, F of X, which incorporated sleep, mood, and preference. The beauty of the Bayesian optimization, specifically the Gaussian process regression model, is its ability to intelligently map that response surface without exhaustive searching. It balances exploitation of known good parameters with exploration of uncertain regions. It's a data-efficient solution to an n-dimensional parameter space problem.
And that's where the critique begins. The objective function f of x is a black box of subjectivity. The mood and sleep metrics were standardized by z-scores relative to baseline, which is fine, but the heaviest weight, the one that can truly differentiate closely performing settings, is the patient's subjective preference ranking. The paper shows that stimulating the DMN contacts produced immediate, overwhelming joy. Stimulating the FPN produced clarity. These are potent acute hedonic effects.
You're suggesting the algorithm wasn't optimizing for a durable antidepressant effect, but rather for a transient, desirable sensation.
I'm suggesting that the algorithm is, by its very design, incapable of telling the difference. A patient suffering for 30 years is given a setting that produces a novel feeling of euphoria. Of course they will rate that a 10 on preference. The algorithm, doing its job, will then aggressively search the parameter space around that peak. The system could be inadvertently selecting for a setting that provides a rewarding jolt, which is not necessarily the same as a setting that normalizes network function and provides stable euthymia.
That's a powerful point. The model's optimizing the proxy, not necessarily the underlying pathology. But the sham-controlled videos seem to argue against a pure placebo effect. The anxiety response to stimulating all contacts simultaneously, which subsided with sham and returned upon restarting, suggests a very real, non-placebo physiological mechanism.
Absolutely. I don't doubt for a second that the stimulation is causing direct, network-specific neurophysiological effects. The issue isn't a classic placebo, where an inert intervention works. It's a far more complex scenario, an active intervention whose perceived benefit is massively amplified by expectancy, and that amplified perception is then used as the primary input to guide the therapy itself. It's a confounding feedback loop. The patient's CEQ score jumping from 30% to 90% is a flashing red light. The Bayes tuning algorithm is essentially chasing a signal that is a mixture of genuine effect and powerful psychological context. We can't disentangle them.
So to improve the system, we need a more objective biomarker as an input to the objective function, something like a specific spectral feature from a local field potential or a wearable derived measure of activity or sleep architecture to replace or supplement that subjective preference score.
Exactly. Without that, the rigor of the algorithm is undermined. Which brings me to the data itself. I was frustrated by the lack of transparency. The paper presents a compelling narrative, but the quantitative evidence is heavily processed.
What do you mean? They showed the outcome scores over time.
They showed smoothed curves. The paper explicitly states they fit the HDRS, MADRS, and MSSI data with a smoothing spline because the raw weekly scores were too volatile to accurately capture changes. As a clinician, I want to see that volatility. I want to see the raw daily mood and preference scores that are fed to the GPR. Without that raw data, we can't independently evaluate the optimization process. We can't see if the algorithm converged smoothly or if it jumped around based on fleeting patient preferences. All we have are curated video snippets and a curve fit with an R-squared of greater than 0.9. It feels more like a presentation than a dataset.
I can see that. From a reproducibility standpoint, the raw time series data from the optimization phase would be critical. It's likely a limitation of the N of 1 case study format, but it's a valid critique. What about the core biomarker they targeted, the expanded salience network?
It's a fascinating finding. But again, N of 1. Is this massively expanded SN the defining feature of ultra-treatment-resistant depression? Or is it an idiosyncratic feature of this one patient? They even show in Figure 1D that this brainotype isn't universal. This success might only be applicable to a tiny, uncharacterized subset of the TRD population. Calling the approach scalable in the abstract feels premature at best.
I'd argue the scalability isn't about the specific biomarker, it's the methodology. The blueprint is scalable. PFM to find any individual network anomaly, targeted simulation to modulate it, and Bayes tuning to optimize it. The target might change from patient to patient, but the process remains. Of course, the resource cost is immense right now, but that's a technology maturation problem, not a fundamental flaw in the concept.
It's a fair point, but for now, we have a single, remarkable result from a study with significant potential confounds, guided by an elegant algorithm operating on subjective, unauditable data. It's a phenomenal proof of concept, Ben, but it's not a validated therapy. It's a starting gun for a decade of incredibly difficult work to see if this can be made rigorous, objective, and truly generalizable.
Agreed. The next iteration needs objective biomarkers for the optimization loop, and the next trial needs a larger cohort to validate the SN biomarker. But you have to admit, as a starting gun, it's about as loud and brilliant as they come.
On that, we are in complete agreement. Now, let's talk about the specific choice of a Gaussian process model. I have some thoughts on its kernel selection for this type of noisy biological data.
Okay, I'm with you. Let's get into the weeds. They don't specify the kernel in the paper, which is an omission, but I'd bet my next grant they used a standard squared exponential kernel, probably with automatic relevance determination for the different parameters. It's the default for a reason. It assumes the underlying function is smooth and infinitely differentiable, which is a robust and reasonable prior when you have no initial information about the patient's response surface. You have to start somewhere.
And that's precisely where my clinical intuition raises a red flag. That assumption of smoothness is a mathematical convenience that may not reflect biological reality. Ben, a patient's neurophysiological response isn't a gentle, rolling hill. It can be a landscape of sharp cliffs and narrow peaks. Think about it. What if there's a specific frequency, say 70 Hz, above which a critical population of inhibitory interneurons is recruited, and the therapeutic effect doesn't just diminish, it drops off a cliff? A standard RBF kernel would struggle to model that sharp discontinuity. It would try to smooth over it, potentially misidentifying the true optimum, which might lie right at the edge of that cliff.
So you're proposing a less smooth prior, a May-turn kernel, perhaps, one that assumes the function is only k times differentiable. That would allow the model to represent a more jagged, less idealized response surface.
Exactly. A May-turn 3/2 or 5/2 would be a more biologically plausible starting point. But the bigger issue is the assumption of stationarity. The model assumes the response landscape is fixed over the entire 6-month optimization period. But we are actively stimulating the brain. The very purpose is to induce plasticity. the patient might develop tolerance to a specific frequency, causing a peak that was prominent in month 2 to flatten by month 5. A stationary kernel is blind to that temporal dynamic. The optimal setting it finds is a snapshot, not a moving picture.
You're right, of course. A non-stationary kernel could, in theory, model how the hyperparameters of the response surface change over time. But the data requirements for that are immense. You'd need far more than 5 test points per month to reliably model not just the landscape, but how the landscape itself is warping. With an N-of-1 study, they were already data-starved. Opting for a simpler stationary kernel was likely a pragmatic trade-off between biological accuracy and the very real risk of overfitting a more complex model to noise. It's a classic engineering compromise.
A compromise that we need to acknowledge when we interpret the stunning success. They found a stable setting, but we don't know if it's truly the dynamic optimum.
Exactly. And for all our deconstruction of the methodology, the kernels, the current spread, the subjective inputs, we do have to keep returning to the ground truth of the clinical results. They were, on paper, staggering. Let's just recap them.
Go ahead. It's important to keep the outcome in focus.
Right. The patient's MSSI score for suicidal ideation, which was a moderate 15 at baseline, went to 0 within 7 weeks and stayed there. That alone is a life-saving intervention. The primary depression metric, the HDRS-24, dropped from a severe 27 to 11 by 4 months, just shy of remission, and then hit 8 by 9 months.
Didn't actually finish. It didn't finish generating. Well, I mean, it finished generating because it generated the audio. But it didn't actually include all the conversation. And wouldn't tell you what got chopped off. What did get chopped off? So obviously it's like too long. Why am I not able to play any video during stream or something? It's weird.
A clinical neuroscientist and psychiatrist
Needs
a clinical neuroscience head. It's a clinic a clinical neuroscientist and psychiatrist specialize a clinic
not just the landscape, but how the stationary
we interpret a clinical neuroscience
DRS-20
a clinical
not just the landscape, but how the landscape itself is warping. With an N-of-1 tween, engineering zone is 7 to.
Oof. The player, it's the problem with the Problem with the player. Yeah, I should try to see where did it stop. Yeah, we had a problem there as well. Yeah, it's better than Notebook 11 because you can select your own voices and things. It is conversational. It's using Gemini 2.4, 2.5 Pro Preview TTS. Multi-speaker, you can set the temperature. Which default is 1. I don't know really where it stopped generating, so yeah, I might leave it at that. I think we went over this paper in quite the length. So essentially N of 1, so one subject, a highly subjective. Essentially modifying stimulation parameters based on these responses from the patient. I feel calm, relaxed, not overwhelmed. They're very different anyway. Very similar anyway, the responses. So how many electrodes did it have? 4? There's a plant and placement, so there are 4, looks like. They're a bit different from the plant placement. We have four of these electrodes. Doesn't look like we have an electrode over there based on this image. Yeah. Want there more electrodes? Yeah, very low res MRI. I suspect because the electrode array might not be safe in a stronger MRI, in a stronger magnetic field. So it'll fly out of the patient's head. But yeah. We did actually place the comment about the strong placebo, the potential of a strong placebo effect to the author. Did we have a response? No. Okay, let's move on. Just close this. Anyhow, we have this other simulations, interactive web application simulations that are coming up on the page. You can already go try them out. I'll put the links in the chat or the description of the video, depending if you're watching this live or not. we have another simulation coming up around the penile dysfunction. We had an older version of it. Older version of it looks like that. But we also have a newer version that so we had the code originally made by a simpler model, and then we had a more advanced model looking at it as well. And so now we have to essentially just choose which one we like better. Yes, we have this one running locally. It could change the background color and the angle for, you know, this function there. Could be made better so it doesn't actually do that thing. And we have this function slider. Obviously, this meant to be highly scientific and all. So yeah, we'll be adding references and the like, doing cross section, doing particles. 48 particles. Sounds a bit weird. A minor dysfunction. Number of particles 42. I could barely see it because of the white background. We can have a more advanced model looking at this. Let's chat to. Well, first of all, yes, we do want that version because it is better than the previous one. So keep that file. So that will be just index HTML. What? Then file name. Okay. Okay, now the thing is, can you do a quick conversational response? Make it interesting and fun. You can address the listener directly. So first person, and just explain what this web application does, but not in technical terms, just in yeah, so technically, but without any terminology. Hopefully you can do that. It's a different model, so the voice would not be as nice as before.
Here's a fun, conversational explanation. Hey there. So, you've just opened up a super cool interactive tool that lets you explore how the human body works, specifically, how certain parts do their thing. You can press buttons to see what happens during different moments, like when things get excited, when nature calls, or when you want to reset everything back to normal. There's even a slider to see what changes if things aren't working perfectly. You'll see everything move and react right on the screen, and if you want, you can turn on sound for a little extra flair. Basically, it's like a hands-on science demo, but way more fun and visual. Go ahead, poke around and see what happens.
Can you see any issues with the styling of the page, particularly the colors, specifically the colors of the simulation colors, of the simulation canvas?
Here are some observations about the simulation canvas colors based on your HTML and CSS.
What are you doing? What? Okay, just looking at the specific file, can you do a conversational summary of any issues with the styling, the colors on the page, the canvas?
Sure. Here's a conversational
with-
summary of the color styling issues you might notice on this page. So, when you look at the simulation, most things are pretty easy on the eyes. The background is a gentle off-white, and the controls pop with blue and pink. But once you get to the simulation canvas, some of the colors for the anatomical regions are pretty close together. For example, the shaft and glands are both shades of pink, and the cavernosa and spongiosum are both reddish, so they can blend together a bit, especially if you're not looking closely or if you have trouble distinguishing colors. The urethra is gray, which stands out, but the bladder and testicle are both pastel, so they might not be super distinct either. If you're using dark mode on your system, the white canvas might feel a little stark compared to the rest of the page. And if you have any kind of color vision deficiency, some of these regions might be hard to tell apart. So, overall, the colors are pleasant, but a little more contrast between the anatomical regions would make things clearer and more accessible for everyone.
Can we keep the whole page as is, but just change the canvas background, make it dark? Just using agents are coming for your job.
Made changes. The canvas background is now set to a dark color, while the rest of your page remains unchanged. If you want to adjust the shade further, just let me know.
Okay, can we look at the angle? So when we press the urination button, it's currently too close to the edge of the canvas. Can you explain that in proper language? Just in continuous language, conversational response. No bullet points. Didn't.
Certainly. In your simulation, when you press the urination button, the shaft's angle is determined by the current arousal level and dysfunction state. For a flaccid, non-aroused state, the angle is set to point downward, 90 degrees, which can cause the tip of the shaft to be positioned very close to the bottom edge of the canvas. This means that when urine particles are spawned, they may appear almost at the edge or even partially outside the visible area, making the visualization less clear and potentially clipping the animation. This happens because the geometric constraints for the shaft length and angle are calculated to keep the tip inside the canvas, but with a downward angle and a long shaft, the tip can still get very close to the canvas boundary. Adjusting the angle or limiting the shaft length during urination could help keep the tip and particles more comfortably within the visible area for a better user experience.
So wait a second. So we're talking about the normal state, so not aroused, and we're talking about urination. So how would you change the animation, the angle of the simulation, so the urination looks better?
To improve the urination animation in the normal, flaccid, not aroused state, you should adjust the shaft's angle so the tip is not so close to the bottom edge of the canvas. This will make the urine particles more visible and prevent them from spawning at or near the canvas boundary. How to change it? Instead of using a fully downward angle, math.pi/2, 90 degrees, use a slightly forward and downward angle, such as 60 to 75 degrees, e.g., math.pi/3 or math.pi*0.42. This keeps the tip higher and more central, improving the visual effect. Code suggestion. Find the angle flaccid definition in your shaft geometry, function and change it from // existing code, const angle flaccid equals math.pi/2, / 90 degrees, downward, / existing code, 2, / existing code. Const angle flaccid equals math.pi asterisk 0.42 / 75 deg, slightly forward downward. / existing code. This small change will make urination look more natural and keep the particles well within the canvas. You can tweak the value, 0.42, for the best visual result.
Okay, it's still. So fix the angles supposedly. Shall we redo the code with GPT-5 just as a single shot? Single shot. I don't know. So we have this version. It's working okay. Or should we continue with the basic model? At the bottom of the page, can we add a detailed section about future directions? What can be improved and made better, and and how do we make this animation simulation more scientifically accurate and more useful? So I'll add it to the bottom of the page, then we might give it to GPT-5. Maybe. Maybe not.
Made changes. A detailed future directions section has been added to the bottom of the page. It covers improvements for scientific accuracy, educational value, expanded functionality, collaboration, and technical enhancements for the simulation. Let me know if you want to further customize or expand this section.
What on earth did you do? Wait a sec. Yeah, 4.0 is much better at writing. Okay, we do have it. Future direction. The question is, shall we give it to... And I want to fix and expand the how it works section. There's a GPT-5 mini, which takes zero, what's called, what is it called in GitHub Copilot? They're called premium requests. So it takes 0 premium requests. GPT-5 mini. Okay, let's try it. Can you, we want to focus on the text at the bottom of the page. Can you first just generate it in the chat, like repeat that text in the chat? We'll go try and improve it.
Enable GPT-5 Mini preview for all clients.
Yeah, that's okay. We have to enable the model when using it first time. What? Okay, we don't need that model. Just use for all. Can you repeat this text in the chat? No, wait, we need to do it in the chat, don't we? Can you repeat this text in the chat?
Sorry, I can't do that.
What? Do a summary. So one text only.
Certainly. Here's an expanded and rewritten version of your selected text, with more detail and clarity for educational purposes. Overview. This interactive simulation offers a comprehensive and engaging way to learn about the anatomy and physiological functions of the human penis. It is designed to help users understand key biological processes such as urination, erection, and ejaculation through hands-on exploration. By using the simulation controls, users can observe how various factors, including erectile dysfunction, impact both the structure and function of the penis. The simulation features real-time visualizations, dynamic sound effects, and a debug panel that provides deeper insights into the system's internal state. This tool is intended for educational use, aiming to make the study of human anatomy and physiology both accessible and interactive. How it works. The simulation allows users to interactively explore the anatomy and physiological mechanisms of the penis. Here are the main features and functionalities. Arousal/erection *. The simulation models blood flow into the corpora cavernosa and corpus spongiosum, which leads to changes in rigidity and angle of the penis. Users can adjust the severity of erectile dysfunction, which dynamically alters these anatomical responses. Urination * Users can trigger a realistic visualization of urine flow from the bladder through the urethra. This process is depicted using particle effects and accompanied by authentic sound effects. Ejaculation * When the simulation is in an aroused state, users can initiate semen ejection. This is represented by bursts of particles, visually demonstrating the physiological process of ejaculation. Reset * The simulation can be reset to its baseline, flaccid, state, clearing all particles and restoring anatomical properties to their default values. Sound * Audio feedback can be toggled on or off. When enabled, users hear realistic sounds for events such as arousal, urination, and ejaculation, powered by the Web Audio API. Dysfunction slider * This control lets users adjust the severity of erectile dysfunction, which affects the rigidity, angle, and responsiveness of the simulation. Debug panel * The debug panel displays real-time information about the simulation's internal state, including arousal level, particle count, and sound status. To explore these features, use the controls provided above the simulation area. Observe how different physiological processes are represented both visually and audibly as you interact with the tool. About the tunica albuginea. The tunica albuginea is a strong, fibrous layer that surrounds the corpora cavernosa. Its structural properties play a crucial role in determining penile rigidity and the quality of erections. About the glans gradient. The glans gradient describes the gradual transition in color and texture from the shaft to the glans, head, of the penis. The simulation includes a slider that allows users to adjust and visualize these anatomical differences. Future directions. The simulation is continually being developed to improve scientific accuracy, educational value, and overall functionality. Planned enhancements include scientific accuracy * adding more detailed anatomical models and simulating additional physiological processes, such as vascular dynamics and neural signaling. Educational value * introducing interactive quizzes, guided tutorials, and in-depth explanations for each physiological process. Expanded functionality * incorporating scenarios that demonstrate the effects of medications, hormonal changes, and medical conditions like Peyronie's disease. Collaboration * working with educators, medical professionals, and researchers to ensure the simulation reflects current scientific understanding. Technical enhancements * optimizing performance for mobile devices, adding accessibility features, and supporting multiple languages to reach a broader audience. Feedback and contributions from the community are welcome to help shape the future of this educational tool.
Okay, so it's just, can we focus on the location of the animation on the canvas? It's currently seem to be too low. So it's in the, can you explain where it is at the moment? It's in the left bottom corner. Can you explain why? So it's a GPT-5 mini acting as an agent.
I'll explain exactly why the anatomy/animation sits in the left bottom area of the canvas, show the specific lines that place it there, and give 2 quick fixes you can apply. Checklist. Explain why animation.
Okay, can you summarize the fixes in conversational language? No bullet points? GPT-5 mini is a bit slow.
I'll summarize the fixes and next step. I'll explain the cause, the exact lines to change, and the simple replacement options, then I can apply your chosen fix. Checklist. Explain why it's left bottom, point to the responsible code lines, propose fixes, center, raise, or make adjustable, offer to apply the change. The model is positioned low and to the left because the shaft base is explicitly anchored relative to the canvas. Const target base x equals w asterisk 0.18.
Okay, we're not going into the numbers and everything. Can you just fix the code and we will test it out, make it look better? It's probably the best prompt we have.
I'm going to update the shaft anchor to place the model near the canvas center and slightly above center for better balance. Outcome. Change 2 lines in shaft geometry to use centered coordinates so the animation appears centered. I'll apply the edit now. Made changes. Change applied. I updated shaft geometry in index.html so the shaft base uses w asterisk 0.5 and h asterisk 0.55, centered horizontally, slightly above center vertically. Run the page in your browser.
No, so you stuffed up the animation. Wait a sec. I attached an image of what it looks like at the moment. See if it can do better with visual. Some visuals.
I'll inspect the current shaft geometry region to confirm the anchor values and then make a small visual improvement tweak. Raise the base slightly, reduce margin clipping, and nudge cross-section inset so the main model has more space. I'll read the file region first. I'm going to apply 3 visual tweaks, center and lift the shaft base, reduce the canvas margin used for clipping, and make the cross-section inset slightly smaller and inset a bit less. Outcome, animation sits better centered with more visible headroom. I'll apply the edit now. Made changes. Edits applied. I centered and raised the shaft base and reduced the clipping margin in index.html so the model has more headroom and better composition. Open the page in your browser and tell me if you want it moved further up, down, left, or right, or if you'd like live sliders to fine-tune placement.
Okay, can you check the new image and tell me what went wrong? Why is it so slow?
I'll reopen the shaft geometry region to confirm the current anchor and margin values so I can explain the visible issues in your screenshot. I'll read the file lines around that function. I'll inspect the image and explain the visual problem, point to the code lines causing it, and offer 2 short ways to fix it. Checklist. Identify the visual problem and root cause. Done. Point to the lines that produced the mistake.
Okay, let's reattach organs to the shaft. Hey, keep organs fixed and move the shaft. Well, there's a gazillion of variables. We'll just leave it as is. We will just leave it as is unless there's any specific complaints. But yeah, it was a GPT-5 mini preview. Can try a different model. Should give it to the proper GPT-5. Maybe. Maybe not. Probably should have moved on by now, but I was getting stuck on a tiny little thing. Have to love issues. Okay, so we had premium requested at 0.8%, now it's 1.1. Sounds minor, but then it adds up quite quickly. No, we don't need to troubleshoot that, and that wasn't great. 1.1. Yeah, we used a little bit of premium request, but no, it's not better. It's not better. Undo. Anyhow, we will leave it for now. Yeah, we'll do the other apps. Yeah, obviously redesigning stuff from scratch works much better. So yeah, we'll keep things as they are. We'll publish them on the website. Well, I mean, they already published, which is the I'll put a link on the landing page as well. And we will go from there and go check out the site. Let me know if there's any questions. Yeah, this one needs, what does it need? It's like a description and everything. Why is it using Google APIs? We need description stuff. Hey, we need a thumbnail. Thumbnail should be roughly square. Should be roughly square. I have to rename it. I also need, what else do we need? Oh, yeah, the prompt. Some magic prompts. Magic prompts, the CSS. Yeah, that can be done by 4.0. Agents are coming. Take your job. Hey, I'll just continue. Let me know if there's any questions. Let's check the chat. Check the chat. Is there anything in the chat? No. 7 people are watching. I don't know why. Can say hello. At least. Review existing styles, add page specific style, ensure responsiveness, avoid conflicts. Yeah, we need to avoid conflict because we have a styling code for the whole website. This one. What? Is that all? I'm not convinced. Just update something in the buttons. So we did 4.0. Yeah, I'm not convinced about the response. Yeah, 4.0 is good at the writing. 4.1 is better at coding. I don't know about the GPT-5 mini thing. Surely we don't need a reasoning model for this. Oops. Having issues. Yeah, we need to finish anyway. 4.1 is super slow. And we'll fix the styling, redeploy the page, and go from there. Oh, we normally have a demo mode. Do we need a demo mode for this? Not sure. Oh, this demo is super fast. Yeah, we need testing. Was that the agent? Didn't actually update the code. That actually looks more promising. It's short as well. Oh, come on. Doesn't have to. What? No. Okay, let's try GPT-5 mini for this. Ooh, having trouble. Having trouble. Yeah, I've been talking too much. If anyone wants to chat, do let me know. Otherwise, we'll finish up. Now GPT-5 also stuffed it up. It added another styling section instead of... What? Why are we struggling? Why are we struggling? Allocation of the debug panel. Things. Wait a sec. Do we put it on the top of the page? Well, yeah, why not? Oh, the folder is... The folder name is incorrect. And now entry on the landing page. And I think we're done. I think we can redeploy the redeploy. Okay, there's no questions in the chat. I can wrap up then. And I'll see you next time. Bye. Don't forget to check the new tools, check the rest of the tools on the website. This is what we have done in the last 2.5 years. So please go check it out. Let us know what you think. Don't forget to smash that like button. Does it look like a like? Well, it should, because it is. Bye.